Hello everyone, my name is Christoph Reich from TU Darmstadt and I'm going to present our paper, Differentiable JPEG, The Devil is in the Details. This is joint work with Biplob, Deep and Chuck from NEC Labs. JPEG coding is used in millions of devices and is part of many real-world image processing pipelines. JPEG takes in an original image and encodes the image into a compressed file. Performing decoding recovers the original image in the form of a distorted JPEG-coded image. However, due to quantization and other discrete operations, JPEG encoding-decoding is non-differentiable. We challenge this non-differentiability and present a differentiable JPEG approach. JPEG encoding utilizes the rounding function for quantization. However, the gradient of the rounding function is 0 almost everywhere or undefined at jump discontinuities. As JPEG uses unsigned integer arithmetic, values above or below the value range are clipped. However, clipping leads to a zero gradient for clipped values. Both rounding and clipping inhabits the application of JPEG and gradient-based learning systems, such as neural network training. Existing differentiable JPEG approaches only model the quantization of the DCT features, which we will show is not sufficient to approximate standard non-differentiable JPEG well over the whole compression range. Our differentiable JPEG approach models all crucial discretization and bounding operations of standard JPEG in a differentiable setting. In particular, we present differentiable circuits for 5 operations using 3 different core functions. First, we model the rounding function with a differentiable third-order polynomial approximation. For approximating the floor function, we shift the rounding function approximation accordingly. To still ensure a non-zero gradient for clipped values, we present a soft clipping operation. Beyond our circuit-based approach, we also present a straight-through estimation approach for differentiable JPEG coding. In standard STE, a constant gradient is assumed during backpropagation. However, our STE approach instead uses the gradient of our proposed circuit functions in the backward pass. Here we validate the forward function performance of our differentiable JPEG coding approach against existing approaches. In particular, we measure the similarity between coded images obtained from a differentiable approach and decoded images from the standard non-differentiable JPEG implementation. Our differentiable JPEG approach leads to a better approximation of the whole JPEG quality range. Especially for strong compression, corresponding to low JPEG quality values, our differentiable approach is able to approximate standard JPEG well, while existing approaches fail. In general, our differentiable JPEG approach consistently leads to a better forward function performance. These results can be also observed qualitatively. For a medium compression strength of 50, as shown on the left, both the approach of Shin et al. And our differentiable JPEG approach approximate the non-differentiable reference JPEG-coded image well, shown in the left column. For a strong compression, meaning a JPEG quality of 1, the approach by Shin et al. Does not produce a JPEG-coded image perceptually similar to the non-differentiable standard JPEG implementation. Our differentiable JPEG approach still leads to an accurate approximation. When using STE instead of our circuit-based approach, an even more accurate approximation of the forward function is achieved. In general, STE approach leads to an improved forward function performance over our circuit-based approach. Why validating the forward function performance is straightforward, validating the gradients obtained by differentiable JPEG approaches is non-trivial, as we don't have a true gradient to compare against. As we are interested in providing gradients suitable for gradient-based optimization, we utilize adversarial attacks to demonstrate the backward function performance. In particular, we utilize differentiable JPEG at attack time to craft adversarial samples. At test time, the generated adversarial samples are fed into standard non-differentiable JPEG before being analyzed by the image classification network. If the differentiable JPEG approach offers effective gradients, the generated adversarial images still deteriorate the downstream performance when standard JPEG is used at test time. Our differentiable JPEG approach leads to superior adversarial samples. Interestingly, our STE based approach leads to a weaker performance than our circuit-based approach. As there are many different ways to approximate the rounding and floor function in a differentiable setting, we evaluate our choice of using the polynomial approximation against other possible approximations. The polynomial approximation leads to the best forward and backward function performance. Importantly, using a monotonic approximation is crucial to obtain a strong backward function performance. As when using a Fourier approximation, which is non-monotonic, backward performance is vastly deteriorated. In conclusion, we showcased that existing differentiable JPEG approaches break down for strong compression. We presented a novel differentiable JPEG coding approach modeling all important discretizations of standard JPEG and outperforming all existing approaches. We hope that our differentiable JPEG encoding-decoding approach can facilitate the use of JPEG in gradient-based learning systems. In particular, our differentiable JPEG approach can be used for differentiable data augmentation and can facilitate the optimization of JPEG for deep neural networks. Please check out our project page and paper. We also provide an open source implementation of our differentiable JPEG approach. We hope you find our implementation useful in your work. Thank you for watching.